Good morning, everybody. I'm back today to present this lecture about how to implement forces on the cells inside CompuCell3D. This is another tool that CompuCell brings to you to help you build your simulation to turn your simulation more realistic. Remember, this workshop is being live streamed on YouTube and recorded to be distributed later. Okay. Um, as usual, here is the outline of the lecture, the talks. And what you see in the head frame is what I'm going to cover today. Usually this lecture it's a bit longer, but since we had to split our there's a lot of time today with Michael. I will shorten it. And the last part, the green frame, it's left as exercise if you want, or just download the lecture from the students' materials and you can follow this exercise. Okay? Okay, let's go. Uh, the motivation then for the implementing of forces at the single cell migration process in biology. Of course, you have to answer a big question, like Professor James uh, remembering the talk, in his talk. The question is, how do the living cells, isolated or collectively, move around within their environment? Okay, this is the question we are trying to answer. And we know that the crawling migration movement is a ubiquitous process, ubiquitous in many biological processes. For example, I can enumerate some of them: the embryonic development, like the gastrulation formation here. You have this picture, the cells moving a lot to change the structure of the blastocell till you have this uh, final situation here with the beginning of the spine of the animal. Then you have wound healing. If you have some injury, the cells in your blood runs to your injury and try to close it. It's another useful use for cell migration. Inflammatory response. If your injury gets to be infected, then you have to cure that infection. Then the immune system will act. And finally, if you are unlucky, you have a cancer metastasis, which is a very important migration movement for the cells when they leave the blood vessels and install in any organ of your body. Okay? And of course, there are many pathologies, but those are enough to have an idea. The follow-up question, how does the cell move? I mean, when you have a cell and you observe the movements in a microscope, you can see different mechanisms for a single cell movement. First ones are the external mechanisms, like here the spermatozoids movement with a flagella, which is an external mechanism. And the other one is a paramecium one, which has this set of cilia around this membrane that makes to move around. Okay, but we can have also internal mechanisms, and those mechanisms that I can enumerate here at least are the lobopodial movement. See, you have this small move here when the cell is in motion with a lobopodial kind of motion. The second one, we have the amoeboid movement. Here you have a cell crawling without not much deformation in his body. There is a little bit, but you barely see in this movie. And the final one is the lamellipodial movement, which is the fibroblast movement you can see in this right movement right here. See, there is this small uh, laser here. Here you can see the a very thin part of the cell, which is a prolongation of the cell, which protrudes and pull the cell forward. Huh? Okay, next, I should mention that our focus today is this kind of motion, the lamellipodial one. Let's see different behaviors among this lamellipodial movement. Here in this picture, in this movie, you can see different behaviors for a cell to move. It's a very fast movie, so it's passing many times. In the first, in this part, we have let's go over. I don't know if I can. This is a diffusive motion. The cell barely moves and keep it in the same place. This is a persistent move. The cells cross the screen. And the other is a mixed one. It's a combination of persistent movement and diffusive motion when the cell stops moving somewhere. See? Okay, so we have those different mechanisms, the behaviors actually. But what mechanism make the cell move? The lamellipodium engine. Let's see here. The laser is there. I cannot click on the page. See, this is a cell, the fibroblast, for example. We have a cell uh, described by four parts: lamellipod, lamellum, body, and tail, uropod. In the lamellum, which is this intermediate part here, you can see here in green at the bottom figure, a mesh of actin and fibers, stress fibers in red here near the cell body where the nucleus is. At the border of the cell, the boundary of the cell, we have a network of actin that form spikes, and those spikes are what make the cell move. You know, the lamellipodium is this red part over here, and inside the lamellipodium there is a bunch of monomers of actin that put itself together in a creating such a kind of structure here where the monomers of the actin deposited the boundary of the cell, pull the cell forward in the up direction here, and at the rear part of the structure, the monomers detach from the structure to be recycled to the front. So there is a kind of treadmill motion here where the structure is being formed and pulling the cell forward in the direction of this force here. You can see this motion in this small movie here, if I can play the movie. Let's see, I have to get rid of the pointer thing. Yes. See here, the monomers are here, and you cannot see they moving, but you can see the spike is being formed here, and the front of the lamellipodium advancing in that direction. Okay, so this is the engine, as you can say, for the migration in a lamellipodial type of movement. Okay, lamellipodium is characteristics of eukaryotic cells. Okay, and the fact that we are going to try to see is such movements like that. See, here we have eukaryotic cells in motion through labellipodial movement. The, okay, one of the characteristics of this kind of motion, lamellipodial motion, or actually for any kind of motion, is the persistent time of motion. What is persistent time? Is the time where the cells choose to move in a given direction, he stays in that direction for a certain amount of time. This is what we call persistent time. In between these big steps, let's say, the cells start to oscillate their membranes or make some diffusive motions and start to move around again. So we have what we call a persistent Brundle walk. And this is what we intend to reproduce in simulations, the persistent Brundle walk. The problem is that, as we could see in the first simulations, for example, that ones about the volume plugin, CC3D cells doesn't have persistent motion. They only move randomly around the position where they were created. Now we have to impose a kind of persistent motion to have this kind of the persistent handle walk. Okay, let's see how we can do that. How do we implement persistence? Oh, well, uh, what we can do is to impose a force acting over the cells. Okay, we are simulate something that imposes force in a given direction, and then the cell will move in that direction. However, CompuCell doesn't have forces in his engine, let's say. The basic of CompuCell, the POTS model, the cellular POTS models, works with energies. But for our luck, differences on potential energies produce force. Like we saw in the when we saw that pressure in a previous lecture, we associate pressure with a force being a derivative of the volume energy. Remember like that? Okay, we are going to the same path here. So, since we have this possibility, we have to include in the effective energy, the cell effective energy, a term that introduces force in that way. Force will be given by a scalar product between, the energy will be given by the scalar product of the applied force times the displacement where that cells make after suffering this force. XY here is the point, the position where the force is applied. In general, we can think that the force is applied at the center of mass of the cell. Okay, so something applies some force applies this force, the cell moves, and at the end of some amount of time we were observing, we measure the displacement and calculate the change in the energy of the system doing this calculation. So we can now see how that is done. Okay, this energy then has the same usual notation product of intensity here, which is the force, times the difference between positions of the center of mass of the cell. This is the term we have to introduce. This is the new plugin we are going to analyze today, the external potential plugin. Of course, lambda is a vector here. We have a vector, a scalar product here. So you have three components in this expression here. Let's analyze it. Let's expand this expression. We have in components uh, performing the scalar product, we have these three terms, x, y, and z, if you are dealing in simulating 3D, for example. For now, for our examples, we are going to simulate in 2D, so we have only to take care of vec x and vec y. Right? These pictures stands for, represents what we are trying to implement. The green object would be the cell, and the red arrow would be the applied force in a given direction. Okay? This force can be decomposed in three components, and then we can implement the force through these constraints, the lambda vec x, y, and z. One attention here is because force derivative, force and the external potential are related by negative, a sign negative. If you want the cell to move towards a positive x, you must have a negative energy in that direction. It's a reminder here. Let's go there. Let's see how to implement then this through a quick example here. So the first, again, I will present here the whole exercise, but I will go on the next slide step by step. Okay, just to have an idea what we are going to do. We are going to create a little bit bigger lattice, create a cell, and include the external potential local flex. Let's put the cell in the center of the system, of the grid, and give it the initial values for the volume plugin, target and lambda. And we are going to use lambda vector equal x and y equals, both components are equals, and equals to -20, okay? Then we are going to accelerate the cell, because at this here, when in the step 4, when we choose lambda of x and y equals to 20, they are constant. So we are applying a constant motion to the cell. But now we want the cell to increase the speed. So we have to change the behavior of lambdas. We are going to calculate the cell speed and make a plot to see how it behaves while the force is accelerating the cell. And finally, we will change the behavior of the cell from a constant value to a random value to see what happens. Okay? Okay, step by step. At the beginning, you open you tweet it. I think I can go faster here because you know how to do that already. You have done that many times. Create a project. I named it E4111. That is the file that you're going to find in the demos code in the website. Specify one cell type, I called MOV, movement cell, or moving cell. Load the plugins contact, volume flex, external potential flex, and center of mass. Finish your simulation. Now, I'm going to be a little bit more slow now because you have to edit some part of the text. What part? The box min and box max of the uniform initializer to decrease the box to make it 10 by 10. 120 to 129, 120 to 129 with the 10. Okay, the 120 to 129, and since we have, let's say, the 256 by 256, this is approximately the center of the grid. So we are putting the cell in the center of the grid using these coordinates here, and the width is 10. Then in the start function of the steppable, we write this line here we make a loop for cell target and cell lambda volume to put the initial values equal 310, and we put the components of the force. Cell lambda vex x, cell lambda vex y, both equals to minus 20.
If people have it working, you could put your results in the screenshot of the results in the chat so we can see what you got. If you need more time or you're confused, please speak up in the chat.
In this case, only one class is created. Yes. Yes, only one. Actually, is very same one that before, but with another name, if you want to. The class receives the project name. Here is the code. I can show you if you want, guys. The XML file with the external plugin potential loaded here, and the uniform initializer with the corrected lines. And in the steppable file, oops, not this one, this one. See, the class received the name of the project. And here I forgot to write this line here. Anyway, I can, in this step function, start function, I can put here in this position, you put these 2 lines here. Yeah? And run the simulation. I can, oops. And every time that I move the player for the screen, the shared screen, something strange happens. And I have to open again. But anyway, I have the movie here. I will just end the poll here, and I think I can move on now. Okay?
Hold on just 1 second here.
I can't find this in CC3 region. Can we add it using any menu? I don't think you can add this lines of potential, lambda potential at the menu. I think you have to put by hand. Let me check. Should be here. Here. Apply force to cell. Let's see if I can do that here then. CC3D Python constraints. Here. Here is the snippet. You don't have the lambda vac x, then let it to 0. And here you write -20 and -20. Very low. Okay? Yes, of course. If you apply too strong force, the cell would uh, be destroyed, actually. Yeah?
Applied force is under explicit force in the pull down menu.
Yeah.
Yes, set vector z to 0.
Yes, we are in 2 dimensions, so you don't have any component in that direction. Yes, you apply force only at t equals to 0 because that will be the value for the constraints all over the simulation, unless you change it later. Yes, it's it in start, not in step. As you can see here in the screen. Okay, let's move. This should be the resulting motion you have. One word about the periodic boundary conditions. See, I think it's the first example exercise you are doing using that periodic boundary conditions. What happens here when the cell reaches the corner of the screen, it disappears and appears in the bottom left corner of the screen and continues motion as if nothing happens. I mean, periodic boundary conditions in a 2D grid is the same as the cell were moving over a tire, a donut. Do you understand that, people? Because if you cross the top border, it will appear in the bottom border. If it appears in the right border, it will appear in the left border. So it's a donut. Imagine a donut when an ant is walking over the donut, eating the sugar. He will never reach the end of the environment. He will keep, the ant will be moving forever there without find any wall. This is what we do when we implement the periodic boundary conditions in this 2D grid. Okay? Okay, this is, again, there is day 4 here. There is no day 4. It's only demo codes. Okay. Again, now you have a persistence. The cell is moving in a given direction at a constant speed, as you can see. Let's change a little bit this. Let's make the cell to accelerate. Okay? So to do that, this is what we have to do now. We keep that start function as is, but we now have to define a time interval for changing the acceleration, the speed of the cell. So we define at the very beginning of the cell, the steppable, a variable which defines what is the time interval. And in the steppable, I include this block here, this frame here. I make a test. Each time that the number of MCS, the Monte Carlo step, is an integer multiple of time interval, the value of the force components will change accordingly with the value of the time step. It's a choice. You could put here any function. I'm choosing because MCS, the time step is increasing during the simulation, so the components of the force will increase also. I divide by same to keep the number not very big and to not have, as someone put in the chat, a big force that will destroy the cell. Okay? So please go ahead and make this, implement these changes. Okay. So let's see the result here. This is what we'll see. The cell starts moving slow and then starts to run, to be faster. Yeah. If someone starts to see at the very beginning barely moves because remember the acceleration is changing by Monte Carlo time step divided by 100, so the increase is very small. But since when you got, for example, 3,000 Monte Carlo steps, your change is about 30. And the cell goes very, very fast. Let's go. Now to calculate the cell speed, because if you note there, it seems that, let me go back a little bit and run here. This one?
Yes, that's what people would like.
Okay, I have to edit here, just a sec. About that statement, if not MCS percent time interval, it means that the MCS percent time interval is a division of MCS by time interval, and it grabs the decimal part of the division, the non-integer part of the division. Okay? I'm saying that if that part is zero, which means that the MCS is an integer multiple of time interval, then you execute the change. For example, if you have 200, 400, 500, then you have 500 divided by time interval, you have 5. There is no decimal part in this number. So you enter here. Now, if you divide the 500 or 50, 525 by time interval, you're going to have 5.25. Then you have a decimal part, and this block is not performed. Well, does anyone can help you, Rodrigo? I think I move on here now. Otherwise, I will not able to finish the.
Yes, in Python, always you must define variables before you use them.
That's why I wrote at the top of the stepable.
Right, right. But I'm just telling people who are having trouble that's a common Python error.
Okay, to calculate the speed, to be able to plot the speed in a graph, we have to calculate the speed as its physical definition, displacement over time. So you have to measure the displacement of the cell in two different instants of time, calculate the displacement, and calculate the components of the velocity. The total, the modulus of the velocity is calculated as this way. The same we can calculate. The same way we can calculate the modulus of the force, the square root of the sum of squares of components. This is how do you calculate the modulus of a vector. Okay? And now you have to implement this in the code. This is a little bit complicated. Again, we have to introduce now to enters in the cell dictionary. Remember the cell dictionary that Pedro commented yesterday? To store all the position of the center of mass, the coordinates of the center of mass of the cell. You can use the same code you are using so far, okay? Just to not start a new project again. I have a very new one in the student materials. You can download if you want. But here, this is what you have to include. 2 dictionary entries, old XCM, old YCM. The first definition is in the start function of the stepable, because when the simulation starts, this dictionary will contain the initial cell the center of mass coordinates. The follow lines are the graphs too. Now you know how to put the graph. Go from the drop-down menu, include the graph, configure it like cell speed in the title, X title lambda back, Y title V. That means we are going to plot V against force, or modulus of V against modulus of force. You can see how the increasing of the force affects the speed of the cell. For those who had already finished, I will let this slide here. And I will put the next modification you have to include in the code, which is this one. Let me move around here. This. To calculate the speed now, remember the definition, the speed is uh, delta displacement over time. So we have to, here, we make a loop. Well, we have that loop where the force is being changed. Be, just below the instructions for changing force, we include this yellow frame here to start. We calculated the displacement as the actual position of the center of mass minus the old position, which is stored in the dictionary. Then we have the x displacement. Now, we have to be carefully because we are dealing with periodic boundary conditions. Then when a cell cross one of the borders, we'll have to correct the right displacement to bring it to the right grid you are dealing. So, for example, here, see if this if statement, if dx, which is the difference, is bigger than half of the size of the grid, that means that the cell crossed the border, one of the borders, left or right, for the x. Then you have to correct it. Then we decrease that amount for the whole dimension of the grid. Okay, I think it's too much information to get it now, but later you can draw on a piece of paper and analyze this thing, okay? For now, just believe me, we have to do that, otherwise you have a very wrong calculation if you don't correct the periodic boundary condition. The same we have to do for the y component. The displacement is the actual y center of mass minus the old one. And again, we have to test if this displacement cross the border, the top or the bottom border. And we correct to put the cell inside our original grid. Okay? Once you have made this test, we go to the red frame here, where you calculate the speed. Well, the speed is the square root of the displacement divided by time interval in this line here. And the lambda vec, the modulus of lambda vex, is the square root of lambda vec x squared plus lambda vec y squared. So now we have both the coordinates to be plotted in the graph, this one. We are going to plot in the graph we just created before in the start function, the coordinate speed against lambda vec. And finally, we update the dictionary, putting in the old position the now position. Because in the next time we are going to calculate the displacement, those are going to be the old ones. You don't need to use NP because the library already has the SQRT. But anyway, if you load NP, NumPy, it's okay. You don't calculate delta E. Delta E is calculated by CompuCell itself. You have only to update the lambda vax and force as well. This is made internal. You don't need those instructions here, Anastasia. It's a little bit long to type. Okay, I will go on. And this is what you should see. If you run the simulation, this is what you should see. First, at the left panel here, you see that cell is a little bit fragmented because this force is already too big. In the right panel, you see that a cell reaches a maximum unsaturated. Why? Do you know why? Why there is saturation here? The answer is, you know the answer, but I will put here. Whoops, too fast. See, remember the shape of the expression of the potential minus lambda vac times displacement. If you increase lambda vac too much, you decrease the probability function to accept flips. Remember where I showed this in the last lecture when we increase the lambda for the surface or the lambda for the volume, you could not, for the surface one, you decrease the acceptance to almost zero when we increase this value here. So there is no point in to keep increasing the speed, the force, because the only thing you're gonna have is the fragmentation of your cell. There is a limit for that. And you can, from this graph, you can see. Okay. Finally, this one, I think I'm running out of time. I think I'm gonna comment this one and show the result later. Okay. The fact is, in this last part of the exercise, I would change the directionality of the cell. Because so far we have both components change equally, both force components change equally. Now we want that components have random values. So the cell will execute a random motion. And how that is done? Well, we can start a new simulation exactly the same way as the previous one. But now we are going to change a little bit in the contact part of the previous one. We are going to change medium move from 10 to 22 and move, which doesn't make any difference, but anyway, from 10 to 15. It only would be affected if you have more than one moving cell in your simulation. But since you have only one, it's okay. The uniform initializer is the same, and the initial values for target and lambda are the same. Okay? Now the new part. The new part is that we, at the beginning of the steppable, before the definition of the timing interval, we loaded a new library, a Python library called random. And from that library random, we import the uniform distribution, the uniform function. This uniform function, when you call it, It gives you a number inside a predefined interval with a uniform distribution probability. Every single number in that interval has the same probability to be uh, sorted out. Yeah? Okay, then you load that in the steppable, add a graph window to see the trajectory of the cell, and give it the configuration you want. I will use in the x-axis this center of max position, and in the y-axis the y center of mass position. Okay, and the calculation. We in the step function now we change the lambda vector with, where they were constant, they have before constant values, see? Remember they were something like minus 20 each, or minus float of MCS over 100, okay, for both. And now, for each one, I will call the uniform function, the uniform probability distribution. In that interval, I mean, one number uh, in the interval minus 0.27 and plus 0.27 will be chosen, multiplied by 120 here, and the same as here. Since we are calling 2 times the function, both results will be different. Each time you call the function, it gives you a different number. So the lambda vector, the components of the vector will be different. Okay? We don't have time to go to show how to edit the code. And after you run the code, you have this. I think I have one here. Let's see. This one. Oh, no, this one. Let's see if it works. If it opens. No, didn't open. Ah, it's open now. Here. See, the cell is moving there. Each time it changes its motion, I plot the trajectory here. And you can see, this is when they cross the border, there is a little bit a correction that I have to do. See? Then you can track the motion in this way. It's a random walk now, a persistent random walk, because it randomly changes the direction of motion during the whole motion. Okay? And so here is the code is there in the student's materials. You can look. And the final stage is that one. Let me see here. Okay. So I don't have time to go over realistic cells, but if you go to the slide deck in the demo in the student materials, you could see how you can see how to build a cell with more realistic uh, face, let's say, because if you follow this model here, see, or following that structure of the cell like lamellipodium, body and tail, okay, and nucleus, of course, because nucleus must be considered because it gives the cell the volume, basically the cell, and we can construct a cell which has these three components. This way, we create a cell composed by three cells like this. Or instead of one cell, I build three and put it together. And I have to be careful to, when the simulation starts, to have this real structure. Nucleus inside the cytoplasm surrounded by lamellipod. If you don't take much care, you get the wrong cell. You have only this when they start the simulation. Then what you have to do, you have to adjust the contact energies to have the real shape structure for the cell like that. Nucleus in yellow, cytoplasm purple, and lamellipodium is the green part. If you put that to run, make a simulation that put that to run, let's see here if I have this example here, this. Open and play. My player is busy with the first simulation here. Just finished now. Oh, crashed my simulator. Not respond. Good, because I start a new one when this one was work. Let's start over here. Then you can see the final example more. See? You have uh, component, three component cells made by three cells. A warning must be set. Next week, we are going to teach you compartmental cells, which will allow you to build much more realistic cells than this one, because here we have three cells attaching to each other in a way that resemble a real cell. It's a toy model, actually, but it can be used. And here is the last slide I showed you with the random motion, using the random generator to make the cell move, and with a kind of persistent random walk. And I will end the presentation here. And thank you for your attention, guys.